So this shit is not on it. So we can just delete it. Okay. Actually, first, before we do this, I think we should do just for a general refresher. Wait.
Starting with PS5?
Yeah.
Alright.
Not this one though. Second
The
question.
bottom one, right? Yeah.
Okay. So this is a mapping question with a cache size of 4. And it says assume a system with direct mapping of size 4. Complete following mapping chart for each memory access and provide TMA. Calculate TMA if TM is equal to 35 nanoseconds, TC is equal to 4 nanoseconds, and P is equal to 0. So first thing we have to do, rewrite the memory string on the top. Okay. And then we have to index our cache as well. So with direct mapping, the way we do that is we take our current address of the memory string. So,
Justin?
yeah.
You mind making it orientation, or is that not with you right now? The orientation, flip it left and right.
Oh.
Probably look better for the recording. Yeah. Perfect.
Okay. So the way we do it, direct mapping is you take the address and you mod it by the size of the cache. So right now it's 4. So size of cache. And that will get you the index of replacement. Okay. So that is done on misses where we get a read miss. Then we have to find where to replace. Right. So let's see. Also, the good thing with direct mapping is that you don't have to go through the entire cache. You can just go to whatever it's supposed to be mapped to. And if that's not the element there, we get a miss and we replace. So we see address 1, and when there's nothing in the cache, we have to ask ourselves, where is that going to go? So 1 mod 4, that's just 1. So that's going to go in index 1. These are the indexes. Just say that's I. 1 goes there, and that is a miss. 2, nothing there. Miss. 3, nothing there. And if you want, you can rewrite it as well. Like that. So, and then 4 mod 4, that's 0. So 4, 1, 2, 3. And these were all misses because they were never in the cache yet. Then 1 is a hit. So we don't have to rewrite anything. 2 is a hit. But 5 is a miss. Because 5 mod 4 is 1. And 1 does not contain 5, it contains 1. So we're going to replace 1 with 5. 4, 2, 3. And then on the next point, we see we also get a miss because 1 mod 4 is 1, and index 1 does not contain 1. So we replace 4, 2, 3. 2 is in the cache still, hit. 3 is in the cache still, hit. 4 is in the cache still, hit. 5 is not in the cache, so we look at index 1 because 5 mod 4 is 1, and we see index 1 does not contain 5, so we replace 4, 2, 3. That was a miss. 2 still in there, hits. Same reason again, we're going to replace 1. That's a miss. 4, 2, 3, and 2 still in there, so that's a hit. Now, in this answer, we also have to get the TMA, which the TMA is the number of hits times TC plus the number of misses times TM plus the penalty time. So for hits, we have 1, 2, 3, 4, 5, 6, 7 hits. And miss 1, 2, 3, 4, 5, 6, 7, 8. Wait, I missed one. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's good. So 7 hits, 8 misses. So your answer is going to be 7. That's the number of hits. TC is given in the problem, so TC is 4 nanoseconds. Plus the number of misses, 8. TM was 35. And P was 0. So you can just write 35 nanoseconds plus 0. And just leave your answer like that. And that would be the answer for that part. Any questions about that? Or Eric, do you have any questions about that?
No.
Right, and then we have fully associative cache, meaning we just enter in things sequentially. So index 0, 1, 2, 3. Once that's filled, we have to find a replacement algorithm for that. Because direct mapping already has a replacement algorithm, fully associative does not have a replacement algorithm. And same with set associative, X set associative mapping. So, sorry. So it says fully associative cache of size 4 with LRU replacement, meaning we're replacing with the least recently used element for address. So for this question, first thing we do, of course, the indexes. Then we do the memory string. Okay. All right. And then from there, if you wanted to, just to remember, you can go down here, right? Number of hits times TC plus number of misses times TM plus P. So right now we have TC, TM, and P. That's given in the question. And now we just have to find hits and misses. So first, we have 1. Nothing's in the cache, so that's a miss. And it goes in the first spot available, which is 0. Second, we have 2. 2's not in the cache. It goes in the next spot available. Same thing with 3 and 4. Okay. Now for least recent, for direct mapping, if you wanted to, you could write it out like this. But for something like where you need a replacement algorithm, I wouldn't rewrite it because it makes it a bit easier to see what you need to replace if you don't rewrite your things. right? Because right now it's obvious to see that the least recently used was 1, right? But as you get down like here, and if you're like rewriting everything again, it kind of makes it harder to see. So 1, we get a hit. And again, that's just going to go here again. And we're not going to rewrite 2, 3, and 4, right? When you move forward by a 1, least recently used is going to be referring to the 4 previously used, right? Right now we see the most least previously used was 2, then 3, then 4, then 1. If we place something here, then the least recently used is going to refer to this area. We have 3, 4, 1, whatever's here. And then again, it'll continue. So everybody's going to be shifting over by 1. It's a cache size 4. So again, 2, we get a hit. That's right there. 5, we get a miss. So we must replace it with the least recently used. So take a look at the previous 4. And we see 3 is the least recently used. Right? Because it's not used here, not used here. Let's say if it was used here and here, not here, then 4 would be the least recently used, right? But since it's not, it's 3. Oh. So we're going to place 5 with 3. Okay. And then 1, we also get another hit. 2, we get another hit. But 3, we get a miss. So we have to say, what do we replace it with? Well, let's check. Here we see it is 4. Well, actually, technically, it's 4, 5, 1, 2. Ignoring the repetitions, it's 4, 5, 1, 2. So that means that 4 is the least recently used. That's where we're going to place 3. Okay. But then we also get another miss on 4, so we have to say, where do we put that now? We're going to see that 5 was the least recently used because it's 5, 1, 2, 3. So 4 is going to go where the 5 was. Then we get another miss on 5. And the least recently used was 1, 2, 3, 4. So the least recently used was 1. So 5 is going to go where the 1 was. Then we get a hit on 2, another miss on 1. So the least recently used was 2, 3, 4, 5. So we're going to place where the 2 is. And then from that, we get a miss on 2. So we have to replace it with 3, 4, 5, 1. So we're going to place with the 3. So that goes
Justin?
there. Yeah.
Did you skip the 2 with the hit? Because I thought you would place the 3 with the 1.
Wait, what?
The 1, the last one that you just did, would that be at the 3 spot? Wanted to take care of 3 because it's a 2 is a hit, right? So 2 would be the first.
Oh, sorry. Yeah, I forgot to rewrite it. That should go there. That's why it's 3, 4, 5, 2. So from there, 1 will go here. This will be a hit, and that'll be 2.
Wait, so we're always checking the 4 previous terms, right?
Yeah, if you're ignoring repetition, then yeah.
Wait, what do you mean by like ignoring repetition? So like if there's like 2, 2, and then like 3, 4.
So like here, right, at this point here,
Mhm.
we wanted to see what was the least recently used. So we had to look at the 4 recent elements, right?
Yeah.
It was 2, 1, 5. We get another 2, so ignore that. 1, we had another 1 already, so ignore that, and then we get a 4. So the 4 elements we should be looking at is 4, 2, 5. Sorry, 4. Wait, 4, 5, 1, 2. because we ignored this one and we ignored this one.
Oh,
Because
okay.
it was used here and here.
Yeah.
So from that, number of hits is 1, 2, 3, 4, 5, 6. Number of misses 1, 2, 3, 4, 5, 6, 7, 8, 9. So your answer 6. The TC is 4 plus 9. Your TM is 35 and P is 1. So 35 plus 1. And that's the answer. Are there any questions about that? Sorry, let me just open my door. Let me lower my mic real quick. Alright, can y'all hear me?
Yeah, we can.
Yeah.
Alright, so that's problem set 5. Any questions about problem set 5? Alright, and then problem set 6 was this one. Which is basically what we were just doing, but with different replacement algorithms. This one was two-way set associative. Two-way set associative. This one was just direct mapping. This one was fully associative, but I think the difference was I think this one had right back. No, it didn't. Okay. It was mainly just calculating total memory access time using different memory strings, just so you can kind of understand the difference between them. So, I guess should we just do? Should we just do two-way set associative really quickly and then move on?
Probably
Yeah.
saw the difference between FIFO too.
Mhm.
Because remember
Oh,
how
FIFO as well.
and
Okay.
LRU.
So, where am I? Okay, let me duplicate this page. Okay, this one is going to be fully associative. FIFO. This one is two-way set associative with let's go LRU. He said we have to know opt as well, right?
Yeah, I believe so.
Okay, so we'll do another one of that later on as well. So let's do this one first. Fully associated with FIFO, again, we first index and write a string. One, two, three, four, 1, 2, 5, 1, 2, 3, 4, 5, 2, 1, 2. Okay. So this is fully associative, meaning that we're just going sequentially 0, 1, 2, 3. And then what matters is the placement algorithm, which is FIFO. Right, where if you're in data structures, you should know what FIFO is. Or if you have a queue, it's like a line where you're at the first spot. Boom, boom, boom. You can't leave until this one leaves. So he goes, then this one goes, and this one goes, then this one goes. And so on. So let's see. First one in is going to be 1 because we have nothing in the cache, and that's also going to be a miss. 2, nothing in the cache, or in the spot that's supposed to go to, so that's going to be put there, put here. Okay. Then we get a hit on 1, and actually, let me not rewrite it. And we get a hit on 2. But then we have a miss on 5, so we have to know what should we replace it with. Well, what was the first element here that was put in? It was 1. Regardless of us having other hits, we're just looking at what was put in first. So 5 is going to go here. Let me rewrite it just in case. 5 is going to go there, right? Actually, no. Let me not do that. And then we get another miss on 1. And once this has gone out, that means that this can go out. So we're going to place it with this. From that, we get another miss on 2. So the next one out, 3.
Wait, doesn't 1 go there, or?
Oh,
What do you
sorry.
get- Yeah.
That's the right one. We get a miss on 2. Next one to go out is 3, so 2 goes here. And then we get a miss on 3, so 3 goes here. All right. Once we have replaced what is here, we go to the next sequence of first in, first out. So the first one in here is 5, then a 1, then 2, then 3, then it's going to go back up to the top, and continue that way. Okay. That's why I didn't rewrite it here, to make it less confusing. Just think of it as you're just staying sequential, where you start here, boom, 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 back up to the top, boom, 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 until you're done. Right. So number 4, we get a miss. Replaced with 5. That's the first one there. I'll kind of block this off so it's easier to see. So 5 is the first. Then we get a miss on 5 again. So 1 is the first. Sorry, no. 1 is the first, replaced with 5. 2, we get a hit, so we ignore it. 1, we get a miss. First one right here. Boom, that's 2. 1 goes there. We get a miss on 2. So 2 goes here. Because we just finished and went all the way up to there. And after that, if let's say there was more stuff here, this would be first, second, third, fourth. Based on this, we had to get the hits and the misses. So hits, 1, 2, 3, only 3 hits. 4 misses, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the hits, just rewrite it. Hits, TC, oh sorry, plus misses, TM plus P. that's equal to 3 4 nanoseconds plus 12 35 plus 0. That's what was given. And that's your answer. I know people like KT was saying that he couldn't understand what the difference was, but here's one memory string where you can clearly see the difference between LRU and FIFO, where LRU only had 6 hits and 9 misses. This one had 3 hits and 12 misses. Okay. All right.
Yeah, I just wanted to say the cool thing about it is that if there's no hits at all, F FIFO and LRU are basically the same thing. You get the same answer. But once you start getting
Yeah.
hits on your memory string, then that's when they become different.
Mm-hmm. Wait 1 second. Okay. And then now we have two-way set associative. Two-way set associative, what it means is that you're breaking up your cache so that each portion of the cache will only have 2 elements. I believe, right? So let's say if it was 4-way set associative, each set's only going to have 1 element. If it was 1 set associative, then each set is going to have. Wait, no, I'm tripping. Hold on, wait. Is it that the cache will have 2 sets? I forget what it is. Do any of y'all remember?
Yeah, so if it's two-way set associative, that means there's gonna be 2 blocks. So there's gonna be a 0 and a 1 block. But since this is size 4, that means each one will only have 2 inside them. So let's say if it's
The number to the
4,
left of set just means how many sets we have, right?
yeah, it's gonna be 0
Gotcha.
and 1. That's what it is.
So this is 0, 1, 2, 3. What set associative means is, let's say it's X set associative. That means that our cache is going to be broken up into X sets. Here we have 2, so our cache is going to be broken up into 2 sets. So let's go here.
Mir, didn't you say it's supposed to be 0 and 1 and 0 and 1? Or it's 0 and 0, 1, 2, 3?
No, it's 0 and 1. Yeah, like how he's doing it right there.
Oh, so like the inside.
This part here doesn't really matter.
You could put 0, 1, 0.
Actually,
I would put 0, 1 though. That's
yeah, I would put 0, 1, 0, 1.
Alright.
It kind of makes it easier to identify that these are 2 separate sets.
Mhm.
That's done. Let's write our memory string. All right. So with two-way set associative, how we saw with direct mapping and fully associative mapping, two-way set associative is kind of the best of both worlds, where direct mapping is used to determine what set we're going to use, and fully associative mapping is what we use to determine what location we're going to put our element in, right? So to do this, we take the address itself and we mod it by the number of sets, and that'll get you which set we're going to put our element in. I'll just say call it set. So 1 mod 2. What is 1 mod 2?
1.
Okay. Which means that we're going to go to this set. Set 1. From there, once we get into a set, we just use fully associative mapping. Again, fully associative mapping is just sequential though. So the first element goes here, then here. Once we're full, then we use a replacement element. So we're going to put 1 into set 1 at index 0. Because that is a miss. 2, we get a miss. And what's 2 mod 2?
0.
0. Goes into set 0 in the first position of the set, which is 0. 3, we get a miss. 3 mod 2 is 1, so we go into set 1. The next available position is index 1, so that's going to go right there. 4, we get a miss. 4 mod 2 is 0, so the next available position in set 0 is index 1. It goes right there. Then we get another 1, but that's a hit because we go to set 1 and we check if 1's in there. It is, so it's a hit. 2 is a hit, and then we get to 5 and that's a miss. So we have to figure out where that goes. 5 mod 2, that is 1. So we go to set 1 and we see that 5 is not in there. We see 1 and 3. So we have to replace it with one of them. And we see that we're using LRU replacement. The least recently used in this case, between 1 and 3, is 1. Actually, wait, hold on.
It would be 3.
I'm tripping. Yeah, because I didn't rewrite it. That's why.
Mhm.
I would say with LRU rewrite. With FIFO, don't rewrite it. Because FIFO makes it confusing. LRU makes it easier to see what is the least recently used. So let's rewrite 2. Okay. So then we get up to 5, and we see the least recently used is 3. So we're going to place the 3 with the 5. We get another hit on 1, so 1 goes here. We get another hit on 2, 2 goes there. We get a miss on 3. Least recently used in set 1 is 5, so, okay. It's 5, so we're going to place the 3 with the 5. 3 goes here. 4 is another hit. Is there nothing going across? 5 is a miss. Least recently used in set 1 is 1 itself. So 5 goes there. 2 is a hit. 1 is a miss. Least recently used in set 1 is 3. And 2 is a hit. Was there. And I think that looks good.
Last column is 1, 3, or the second to last column.
Oh, sorry. Yeah. My brain is killing me right now. Alright. And then now we have to calculate the number of hits and misses. So hits. Misses 1, 2, 3, 4, 5, 6, 7, 8. Hits 1, 2, 3, 4, 5, 6, 7. 7. So then the number of hits is 7 times the TC 4. I believe it was 4. Plus how many hit misses 8. 8. 35 plus 1. Because here in this one, P is 1, TM is 35. And that's it. Any questions about that? All right. So now,
Is there also like one called opt or what is that?
so there's opt as well. I guess we'll do that really quickly.
Wait, is that a replacement algorithm?
It's a replacement algorithm.
Mm.
So let's go here. We're gonna do fully associative cache with size 4 with opt. Okay. 0, 1, 2, 3, 1, 2, 3. Oh. 2, 3, 4. 1, 2, 5. I think it was 1, 2, 5. 1, 2, 3. Now, opt doesn't really make sense to be used for this string because all of them are used in the future. But let's see how this goes. This is going to be stupid, but let's see. So this is fully associative, and these are all misses. So it's going to look like this: 1, 2, 3, 4. But then we get a hit. We get a miss on 5. So now we have to look into the future and compare what's used the most times. You see, 1 is used twice, 2 is used 3 times, 3 is used once, and 4 is used once. So we get a tie. To break a tie in opt, we use FIFO. Right? We see 3 was put in first, and then 4. Then we're just going to replace the 5 with 3. Okay. Then we get a
Say that one more
hit.
time?
When you have a tie in opt, then you're just going to replace it. You're just going to you figure out what you want to replace it with using FIFO. Right, and then 1 we get a hit, 2 we get a hit, but 3 we get a miss. So we are at this 3 here. We get to look into the future. So we see 2 is used twice, but 4, 5, and 1 are used once. So we get to figure out what do we use, what do we replace with. See that 1 was the first to be put in out of 1, 2, 4, and 5. So I believe we could replace with 1. So 3 would go here. Then 4. We get a hit. Right. 5 we get a hit. 2 we get a hit, but 1 we get a miss. We're at this one. Only 2 is used in the future, so we had to either replace with 4, 5, or 3. 4, 5, and 3. Out of those, 4 is the first one put in. Or actually, wait, hold on. I don't know if we should be comparing it based on the order they were put in here or based on the order they were put in here. If we're going off of this, then we replace with 4. But if we're going off of this, we replace with 3. Huh.
Wait, so Justin, we did so 1, 2, hit, right? So when we were doing 1 and 2, so you see the 5 right there where you put the 5 next to the 3.
The 5, this one.
Yeah, that one right there. So that one, 3 is the first one, right? Because like since 1 and 2 already got hit, right? So we're going on to 3. Then for 1 and 2, it got hit again. For 3, why did you put 3 on the first one? Isn't it supposed to be on the fourth one? Like since that's the
Because we're looking
first one.
ahead.
Oh, okay.
What's that? We have 4, 5, 2, 1, 2. 2
Yeah.
is used twice. We don't place with 2, so we have left at 4, 5, and 1. Based on 4, 5, and 1, 1 was the first one used, then 4, then 5, so we replace it with 1.
Oh, okay.
2, we have to figure out which one's used. 2 is used in the future. Sorry, 1, we have to figure out what's replaced with. 2 is used in the future, so we don't. And then the first one out of 4, 5, and 3 to be put in 4. It's replaced with the 4, I believe. And this would still be a hit, so 2 would go here. And we see with this one,
It's 1, Justin.
oh, what? Oh, bro, I don't know why I keep doing that. 1. So hits and misses. And we see with this, we have way more hits than misses. 1, 2, 3, 4, 5, 6, 7, 8. And misses. Obviously, we're gonna have 4 in the beginning. 1, 2, 3, 4. And like a few more. 5, 6, and 7. So that's 8. 4 plus 7. 35 plus 1. P is 1, 35, and 4. Now, I believe that FIFO replacement was correct. Unless we're going off of here. But I'm not entirely sure. I guess we can ask him about that on Monday. All right. Any questions about that? All right. Just go here. All right. So this question is from one of the exams. It's a messy protocol question. And it says, let me full screen real quick. Okay. It says use messy protocol with direct mapping. Write through, do not allocate on write miss policy.
Which test is this, Justin?
The second one. Fall 2022.
All 22, okay.
Okay. Move my mic ticket. Can you all still hear me?
Yeah.
So then, let me see if I can do this. So now, again, this is direct mapping. So we're going to be looking in specific places. Part A, we're loading the number 12 into address 7. Wait, is that even allowed? What the hell? Doesn't have to be in a register? Is that allowed? I'm gonna assume that's allowed. That's weird. Okay. So loading the number 12 into address 27 on processor 2. We see processor 2 already has address 7. meaning we get a write hit. We also see it is write through on write hit. From that means processor 2, address 27, is going to go from shared to exclusive. First, it's going to go from shared to modified, then from modified to exclusive, but we're kind of skipping over that because we modify the cache, and then we also, since it's write through, we're updating the main memory as well. So since they're equal to each other, uh, you know, it is exclusive from that. They have 26 valid, 25 valid, E 28, 32, 29. And from that, since this was changed and was shared with this, that means now it has the wrong value. So it's going to go from shared to invalid. Y'all can still hear me, right? Because I'm kind of laid back right now with the iPad.
Yeah, we can
No,
hear
no,
you.
we're good.
Wait, so in processor 2, since it's the same in the cache and main memory, it goes from shared to exclusive.
Yeah,
But then
but
in the yeah,
if we weren't updating the main memory and just the cache, then it would be shared to modified.
and it's because we're doing a write through, right?
Yeah, right through.
Okay.
And what was your second question?
Oh
No,
no,
accent.
I was gonna ask why does it go from shared to invalid for processor 1?
Oh, okay. Hold on, why is Grinch DMing me? Give me a second. I'm reviewing. I'm kind of lost. I think she does because we are doing the exam right now. Is Grinch in the server or no?
I'm not sure.
I'm not sure. I don't think so.
I don't. Uh, am I able to send her an invite to here so she can join?
I think you should
Yeah,
be able to send an invite, right?
good. I mean, if she's not like what do you call it? Like if she's not the type to like like some weird person, then we could invite her.
No, she's chill. Uh, today's session just started fall 2022. Okay, I think she might join later, but anyways. So from that, let's see. Then we run line B, and this is a load. This is a load, so we're not going to be dealing with write misses and write hits. We're dealing with read misses and read hits. Okay. This is processor 1, so that means everything here is going to stay the same. Let me just put that as E for now as well. All right, and then here we're loading address 28 into R1. We see in processor 1, we do not have address 28. Sorry, here. We don't have address 28. So we're going to get a read miss. We see direct mapping. Address 28, we have to put into the cache. What is 28 mod 4?
0.
That address right there. And we're also not caring about the data, right? Okay. Yeah. Okay. And then also, 32 is invalid, so we don't have to worry about flushing or anything like that. Okay. We can rewrite our others. Since we pulled the value of address 28 directly from main memory, that means the value in cache 1 is the same as the value in main memory. So from that, it's going to be exclusive. Okay. Well, actually, hold on. Just realized we have address 28 here. I'm gonna check this side. Hold on. We can get a read, so we can share that value. This can be shared. Sorry. E2 shared. So we don't have to go back to main memory. That's gonna be shared. Okay. Because we get a read miss on 28. Processor 2 is going to be snooping that, and we're going to say, "Ooh, I actually have 28. I will just share it with you because I'm exclusive." So I'll just share it with you, and it grabs it. Let's say if this was modified and not exclusive, and we want to grab the updated value of 28, then this would grab it, but then from here, I believe this would become invalid. All right. Part C, we're loading number 13 and address 6 on processor 2 for 26, right? Let's rewrite 28, 25, 27. Okay. Remember that when we're doing a read or write to a cache, and the state of a certain address, if it's invalid, that's the same as saying there is a miss. So from that, we're going to get a miss, and we have to go to main memory to grab the data in that address and put it into our cache. That we're going to grab it, put it back in the cache. It's going to be exclusive because we went right from the main memory and got that data. And we see here, no one on the side had 26, so we weren't going to share it. So it should be 28, 29, 30, 27. Shared, exclusive, exclusive, I. All right. Any questions about that?
Wait, so you said that if the state is invalid, it counts as a miss. So then you just have
Yeah,
to go
you
to main
can.
memory and
If
grab
it's
it.
invalid, you can just see it as a miss.
Okay.
We only went to main memory. Think of it like this: we got a miss, right? And then cache one said, "Oh, I don't have it, so I can't share it with you." So then we went to main memory and got it, right?
Yeah, I get it.
Now let's say if we had a miss and then processor one it had it but it was modified. What it would do is it would flush its value to main memory first, so it becomes exclusive, and then processor 2 would gain that value, I believe. So it would need to be updating it constantly. Okay.
Wait, so if you flush it and then processor 2 gets it, it would become shared?
Um. Sorry, what?
You said that if processor 1 flushes it and then processor 2 gets it, would it be exclusive or would it be shared? I'm confused.
I think since they're both exclusive, then they will both be shared.
Okay.
'Cause it wouldn't make sense to have two of the same addresses
Wait,
as an
but doesn't
exclusive state, because exclusive means that you're the only one with that value.
Okay.
What'd you say, Shmiz?
27? If you see on part C, 27, address 27, one's invalid and one's exclusive. Wouldn't it snoop?
It wouldn't snoop because processor 1 hasn't tried reading address 27,
Oh, okay.
right? It would only become shared if, let's say, this is invalid, and then on the next line this was 27. Then we would see that we get a miss, but here it's exclusive, so from there we can share it processor 1. But
Makes
since
sense.
processor 1 hasn't asked for address 27, we don't share it.
Alright.
Part D, we are talking about address 32 on processor 1, and we see we don't have address 32. Right? We don't have it in either cache. Processor 2, we could immediately just rewrite our stuff. Now, what is 32 mod 4?
0?
There. 2, 29, 30, 27. We had to replace it with the 28. Since we got it directly from main memory, that's going to be exclusive. 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 Right. Okay. And I believe that is it. Actually, let me see. Let me just make sure.
Wait, so just asking, but the exam is gonna be like this and then the other thing we did, right?
Yeah, basically. Let me just double check here. Here we didn't get a write miss, so we don't have to worry about the do not allocate write miss policy. Here this is reading, so we don't have to worry about the do not allocate write miss policy. C, processor 2 with 26. Here, this should be invalid. I'll tell you why it's invalid. Just give me 1 second. Okay. So this is invalid here because we see here, number 26, we're supposed to read that as a miss. So if we do 1326 on processor 2, we get a write miss. And it's do not allocate on write miss policy with write through. If we have do not allocate, that means we're just going to be updating the main memory and not the cache. So 26 here is not touched, and it stays invalid. Okay. And it stays valid here as well because we don't touch 26. Now here we get a miss on this, but it's not a write miss, it is a read miss because it's load, and that's why we change it. And that's the same thing here as well. It is a load, that's why we put 28. Any questions about that? So let's check our answer. Probably some parts of it are incorrect. All right, so let's see. We see part A, we said that 27 goes to invalid. And 27 here goes to exclusive. Let's check. 27 invalid, 27 exclusive. And here, part B, 28 goes to shared, 28 goes to shared. Let's check. 28 goes to shared, 28 goes to shared. Okay. Part C, they did nothing here. They did nothing here because remember we have a write miss. Do not allocate, meaning we're not updating the cache, and this was a write miss. If you wanted to, you could just write nothing, but I'd like to rewrite shit. And I feel like that kind of makes it more concrete that nothing happens. So I would rewrite your stuff. And if you're going to print out the solutions, like this, I would also recommend filling in the blanks that he has there. And then finally, part D, we have 32E. 32E.
Wait, Justin, I have a question.
Yeah.
Why did we have that as E in the first place?
Which part?
Part
Here?
C, right? No, part C, we had address 26 as E, right? You
Oh,
said?
yeah. So
Why did we have it as E?
I accidentally put it as E because I forgot about the do not allocate. If it was allocate, then it would be exclusive, right? Because we would take this, put it into the cache, and then also the main memory. That's why it'd be exclusive. But here, we're just putting it into the main memory and not the cache. That's why it stays invalid. Now, let's say if it was write back allocate write miss, then it would be modified because we're just updating the cache and not the main memory. So the main memory and the cache wouldn't be 1-to-1, and it would just be modified instead of exclusive.
Okay.
Any questions about that? This question's only 16 points. That's crazy. Damn.
Yeah,
Any
I
other
don't know if he's gonna
questions
give us
about that?
multiple questions on the exam because, like, he said he said it's gonna be hard. So
It'll probably be like one of these, but also with main memory, and he's definitely not going to give us a write through because write through is too easy. He's definitely going to give a write back. So practice your write back. Do not allocate a write miss. Actually, no, sorry. Practice your write back. Allocate a write miss. That's the hardest of them all. All right. Any other questions about this before I move on? All right. Okay. This one have anything else? Wait. How many points is this exam out of? This one's only 10 points. 6 points. And 16 points. So I guess this question here is 50% of the grade.
Yep.
And this question here is 50%. So if you got this right, 50 points to you, I guess. So make sure you understand that. Here. Okay, we have a few that we could do. So yeah, this one here is not going to be on the exam. This will be on exam 3. Gotta do these though. All right. This question here is 20 points, and then this question here is 30. So this will be 50% of your grade, and then this question here, I guess, was 50. Well, 30 actually. So these two questions here are more than 50% of your grade. Think of it that way. All right. This one says, consider the following code running in two processors B and A. We're not working with P2 and P1. This is P1 and PA. We're using direct mapping cache using Messy protocol. We're running this program here. And it says assume the following execution sequence. So on processor B, we run line 1. Processor B, we run line 2. Processor A, we run line 1. Processor A, we run line 2. Processor B, we run line 3, and etc. Right? And it kind of explains it more here. For example, A1 means processor A is executing instruction on line 1. Now you have to fill the table below with the states of the cache for each execution. That's 20 points. Right? An execution step. What I recommend is doing this. Going to the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Meaning that whatever the output is on number 1, that's going to be this, 2, that, and etc. Right, so number 1 says we are on processor B running instruction 1. Right? So if you want, you can rewrite that here. We're loading address 6 into R2. Okay. Since we're only working with address 6, we're going to be filling in something here. Okay. At this point here, we see that 6 and 5 are not in the cache. So we have to go get it. Oh, first thing I should note, he'll probably say this on the exam. For this question, you have to come up with your own write-through policy. So for this question, let's use write-through allocate. As you can see, it doesn't specify, but on the exam, he'll tell you you gotta use write through allocate, write through do not allocate, or write back do not allocate and write back allocate. You get to choose your own. Write through allocate's the easiest to work with, so I recommend doing write through allocate because write through allocate you won't have to worry about modified. You're just gonna have shared, exclusive, and invalid. So do write through allocate. That's the easiest. You'll only be giving yourself more work if you do any of the write backs. All right. So we see we don't have address 6, so we're going to go to main memory and grab it. And the state of address 6 from that is going to be exclusive. Is anyone confused why that's exclusive?
Wait, it's
Alright.
exclusive because it's not in the cache set, so you grab it from main memory, right?
We grab it from main memory, we put it into the cache, and since those data values are equal, it's exclusive. Alright. Okay. And then number 2, we're on processor B still, and we're running line 2, so R1 6. If you want, you can rewrite that. Oh wait, sorry, 5. I mean. And we see that we don't have 5 again. It's a low type, so we're just going to go directly to main memory, grab it, and put it in our cache. So that will be exclusive. Okay. Number 3, we're on processor A running line 1. No, line 1 is R2. Load 6. Okay. And we're on processor A. So since we're not dealing with 5 here, that means the cache state here is going to remain as E. We're dealing with 6. So we go into cache and we say we get a read miss on 6. Okay. Since we're calling an address that the opposite cache has, and we get a miss, then the opposite cache will say, hey, I have this address, let me give it to you. When they give it, it becomes shared. Okay? Are there any questions about that? So it becomes shared, and that's it for that line. Number 4 then says, we're still in address 2 and running line 2. That one was R1. Load what's in 5. Right. Since we're working with 5, 6s are going to stay the same. And 5, it's the same thing where we get a miss on A. So B is going to say, I actually have this, so you can have it as well. And it shares it. And it does that because it's exclusive. Right? And 5. 5 says we're on processor B again and we're running line 3. Line 3, we're loading R3 into 5. So storing R3 into 5. So again, we're on B, and we're using write through allocate, meaning whenever we get a hit, we're going to update the cache and the main memory so that they stay consistent. So that when we update address 5 to R3, that's going to be exclusive since it's in sync with the main memory. But address 5 on cache A is going to become invalid now. Okay. Then these will remain shared. Other questions about that?
Can you just go over that again?
Since we're storing R3 into address 5 with a write through, allocate, and write miss. Since it's write through and there's a hit, meaning we're just gonna write through. Write through updates the cache and the main memory. So this value here in address 5 will become updated, and so will the address in main memory. Because of that, they're going to be in sync, and the state of address 5 will be exclusive, and then the state of address 5 on A will be invalid because it now has the wrong value. Okay.
All right, got it. Thank you.
And 6, we're running that same line of code, but on cache A. Right, that's number 6, processor A. Again, since we're working with address 5, the 6s can not be changed. And we see that we're going to get a miss on address 5 because the current state of address 5 on cache A is I. And we treat I's as misses. Since we get a miss, but cache B has that value, we can simply just share it over again. Right? So, actually, wait, hold on. It's not a read, sorry. It's a write. Give me 1 second. This will update to the new value, that being E. This can be invalid. Right? Because we're not sharing any values here, we're updating to a new value. We know that R3 they're technically equal to each other, but don't see them as equals. Think of it just as their own lines, right? So that becomes exclusive, then invalid. Right? Because again, it's right through. Allocate on right miss. We got a right miss, so we're gonna update our cache and the main memory to our new value. It becomes exclusive, and since that becomes exclusive, the other value in cache B becomes invalid. Right? And 7. We're on processor A running line 4.
Justin, quick question.
Yeah.
For process 5, you just updated the cache of address 5 on B, right?
No, we updated the main memory as well. Because it's right through allocate on right miss.
But didn't you say it was a hit?
What?
I got confused. I thought you said it was a right hit because you see that our address 5
Yeah,
already
it's
has.
a hit. It's a hit, but it's right through. It's not right back. It's right through.
Oh, so when right through hit, you update both. Okay.
Yeah.
Got it.
Then 7. We're running line 4 on processor 8. Line 4 is we're storing R1 into 6. Okay. And again, we're just working with address 6, so 5 is going to stay the same. Okay. So again, we're on processor A, which is on the right side. He's trying to confuse you guys. On the right side. And we have a 6 already. So we're going to get a right through hit. We're going to update the cache and the main memory. So this S becomes an E. And since it's outdated now, it become invalid here.
On the left
8.
side for the execution step, can you write down what processor it is? Cause it's like kind of like confusing to know what thing we're on.
What processor we're on?
Yeah, it's just like you see how like we have 1, 2, 3, 4, 5. Like yeah.
Okay. An 8 is B. And we're running instruction 4, so let's again this. And we see on processor B, 6 is currently invalid, meaning it's a miss. So we get a right miss. And for our instruction, it's right through allocate on right miss. So we can just update our cache to that new value and the main memory. This becomes exclusive. And since that becomes exclusive here, this becomes invalid. Invalid. Okay. The 9, processor B, we're running line 5. Line 5 says address 5 to R2. Okay. And on address, on On processor B, we don't have a 5. Right? We don't have a 5, but we have a 5 on A. So when we try to find a 5 on B, we're going to get a miss. A is going to pick up on that miss and say, I actually have that. I can give it to you so we can share it over. Okay.
Wait, so shares are only for like read misses, right?
Yeah.
Okay.
And 10, we're on processor A. Running line 5 again. And we already have the value of A. So we can simply just rewrite what we had before because there was no change. Oh, I wrote that incorrectly. I believe that's correct. Might be an error or two, but let's check. So let's see. I'm gonna scratch my eye. Actually, let me see something.
He's doing do not allocate, so shouldn't it be different?
He did do not allocate.
Yeah.
I mean, you could do whatever you want. So I think our answer will be different
Mhm.
because he doesn't specify. I mean, if we want, we could redo it and do not allocate if you want. But I believe for allocate and right miss, this should be correct. So that should be the answer for allocate. I guess should we do? I want to try it now with do not allocate.
Can you explain the last line though, Justin, really quickly? I'm confused on that one.
The last one here.
Yeah, the last one.
So here from processor A, we're loading address 5 into R2. So we go to processor A, address 5, and we see that it's shared and we have it. So we could simply just give it into R2. So that means everything here is just going to stay the same because we don't change the states of anything. Yeah. I guess let's do not allocate. Okay. The only thing that's going to change is what's inside of here. So for do not allocate, I have to keep going up because we wrote everything here. We're on processor B, and we're saying load address 6 into R2. We don't have address 6, and it's a read miss, so we're simply just going to go to main memory, grab it, put it in the cache, and then put it into R2, so this will be exclusive. Then, still on processor B, we say load address 5 into R1. We don't have address 5, so again, we're just going to go to main memory and grab it. That'll be exclusive. Sorry if you guys hear my dogs barking. And then address, sorry. Bro, this fucking dog. Processor 8, we're looking at address 6. We don't have it. but processor B has it. So processor B can just go ahead and give it because we get a we get a read miss. So processor B can just go ahead and give it. Shared, exclusive. Same thing on line 4. We're working with 5 instead. We get a miss. So processor B can just share it. We get shared. So now we're all of us are currently sharing it now. Okay. Then we're going to go back to processor B and say load R3 into address 5. We get a hit and it's right through. So we're going to update the cache and the main memory. So that becomes exclusive for address 5. But here it becomes invalid. Then we go to main memory. Then we go to processor 8 and we run that same line of code where we're loading R3 into address 5. Okay. Loading R3 into address 5. We see that address 5 is not inside of address 8. So we get a write miss. With this, we have write miss. Do not allocate, meaning we're not going to update the cache. We're going to update the main memory. So this is going to stay invalid. Shared. Since we updated main memory, it's no longer going to be exclusive. So it's going to be S. Sissy. Then line 7.
Wait. So you just updated main memory there, right? Just to
We have just updated main memory, not cache, keeping this invalid, but also turning this invalid. Now, technically, since we're still working with R3, I feel that it should stay exclusive because it's the same value. But that when I originally answered it, I kept it as E, but then I looked at his answer and then he changed it, which I'm gonna ask him about that tomorrow. Sorry, on Monday, but I might email him or something. I'll just be like, what? Like, shouldn't this be exclusive because R3 is the value of R3 doesn't change? But we'll see.
Oh, maybe this might be the question that he got wrong on purpose.
Didn't he say that was just for the problem set, not the answers, not the exams, or was it the other way around?
I thought it was exam, right?
Someone told me exams, and then another person was telling me that it's problem set, and so now I'm just like, bruh.
I can't tell. I don't know.
I have the recording of it. He said problem set.
We did.
Mm-hmm.
Okay, so I guess either what he did is correct, or he accidentally got it wrong. So I'll email him about it tomorrow or something. And then line 7, we're loading R1 into address 6 on processor A. We have 6, so and it's right through. So 6 is going to be exclusive. This becomes invalid. This is still invalid. So now we got I. Right. Then line 8, we're on oh wait, sorry. I did it on the wrong processor. There should be E. Okay, now we're on the right processor. Now we go back to processor B. And we say load R1 into address 6. We don't have address 6. Right? So we get a miss, and it's do not allocate on miss, meaning we don't update the cache, but we update the main memory. Since we don't update cache, that stays invalid. This is 5, so we don't have to do anything with that. But since main memory has been updated, address 6 becomes invalid. Address 5 is also invalid. Okay. Then line 9, we're working with address 5, but we see that this is a load. So we're reading, we're not writing. So we don't have to deal with write misses, we're dealing with read misses. Line 9, we see it says we're on processor B working with address 5. We don't have address 5 because it's invalid, so we go to main memory, grab that value, put it in the cache, then put it in R1 and R2. From that, this part here becomes exclusive. It becomes exclusive because that's the 5. This is I, and this is I. Then we go back to processor A, run that same line of code with address 5. But processor A does not have address 5. Processor B does have address 5, so we can just go ahead and share it. So from that, we're left with ISIS. Any questions about that? Let's go ahead and check it. Compare. Find a good way to compare this. So first 3 lines we have E E E S E S E E S E S. Fourth line S S S S. Fifth line S E S I. Here we have S E S I. What we see here as well, between shared and E, he put modified. This is because you don't have to rewrite it if you don't want to, but to explain it, we're updating the cache first, and then we're going to update the main memory, right? So as soon as we update the cache, but it's not the same as main memory, it becomes modified. But since we go and also update the cache, it becomes exclusive right after. So I don't think you have to write SME. If you wanted to, you could just write SE or just E. I think that would work like this. But that's kind of the explanation for that. And then 6, we have SISI. 7, we have SIEI. 7. Let me see. Oh, sorry. 7, we have IIEI. IIEI. 8, we have III. 9, we have IEII. IEII. Then ISIS. ISIS. That is the answer. Any questions about that? All right. That's the answer for that. That's 20 points. And now we have this one. This is the hard one. We have to deal with messy, we have to deal with mapping, and we also have to deal with write back policies. And then we also have to deal with updating our main memory. So what I recommend when you get this question, 1, 2, 3, 4, 5, 6, number them, and go up here. 1, 2, 3, 4, 5, 6. Right? Did you say KT? I think Clint might do some review like office hours at 7:30. What?
You go to his server because he asked people to vote.
I'm asking about now. Oh, he's just answering questions that people might have about the exams. I don't think he's like reviewing specific topics.
Okay.
All right. And then, so we number them 1, 2, 3, 4, 5, 6. And now we go through them. Right. Number 1. Actually, first let's kind of go over what we have to do here. Let me bring up the highlighter. We see we have the cache. Oh, the cache coherence mechanism for a multiprocessor system uses MESI protocol with direct mapping, write back, allocate on write miss. Right? And it says consider a system with two processors, P1 and P2, with the initial cache state shown in the initial state. Okay. Determine the state of block in the caches of both the processor after each operation for changed blocks only, and any update to main memory after each operation. So he says, again, determine the state of block in the caches of both the processor after each operation for change blocks only. Meaning what we had here, where we were kind of rewriting each part, right? We were writing each part just to kind of make it more concrete, but for this question here, he's saying don't write each part, only write what changes. So that kind of makes it a bit harder to kind of keep track of what you're doing, but that's what he says to do. Okay. All right. So instruction 1, we're on processor 2 and we're storing the number 8 into R1. Okay. Number 8 into R1. We know that this is a ALU operation. We're not dealing with addresses here, meaning that nothing is going to change in our cache at this point. Right. So for that one here, we don't have to put anything. Right? Because remember it said only write stuff down if things change. Okay. Then at R1,
operation because it's not
we're
it's
loading
a
an immediate
R-
value
it's R type basically.
into R1. So it's R type operation. Line 2. And that also means that we're not going to write anything here. Okay. Because here it says for change blocks only, so we're not going to rewrite each data. We only replace it anytime it changes. Line 2, we're loading R1, which at this point here was 8. We're loading the value 8 into address 8. Okay. And we're on processor 1. We see on processor 1, we do not have address 8. So we get a write miss. And on write miss, it says allocate on write miss policy with write back. Meaning we're not going to be updating main memory. We're just going to be updating the cache. First, we check, do we have it here? We do have it here, but it's modified. Meaning it's not the correct value in the main memory. So in order for us to share that value, we have to first flush the current value we're at. Okay. So to do this, we're going to go from modified to exclusive with the value 45. So we're going to go here, address 8, and put the value 45. Okay. And then here, again, we don't have R1. Sorry, again, we don't have 8. Here had 8, but we're not dealing with reading, we're dealing with writing, right? So we updated the value in main memory, and then now we're also going to update it here. Okay. So actually, technically, we're not going to update it there because it's allocate and write miss with a write back policy. So, and we have a direct mapping as well. So what is 8 mod 4?
0.
So we're going to place it with address 4. Go here. And that is with data 8. Okay. And since we're not updating main memory, we're modified. Oh, I wrote that on the
Where
wrong
did the
spot
data
here.
8 go? Where did you get the data 8
Hold
from?
on. I meant to do this here. Give me 1 second. Sorry, what'd you say?
Where did the data 8 come from?
Oh, wait. That's in processor 2. It should be 1. Apologies. I'll explain why it's 1. It's 1 because if you see here,
Yeah,
you can assume each register is initialized to value 1.
Mm-hmm.
And we store value R1 in processor P2. Right. Oh, that's also why this becomes invalid because we're working with different registers on different processors, right? So that's why it becomes invalid there as well. Okay. Just give me 1 second. Let me just check something real quick. I believe it's this one. Okay. Not a memory. Huh. For some reason. Oh, okay. I understand. So this is going to be a bit weird. Bear with me. So at this point here, again, we go from we go from modified to exclusive, right? Where we flush whatever we had into main memory. But then here, we're also requesting that. So we share it. This spot here becomes shared. And then we load that value R1, so it becomes modified. Since this modifies what we had before from when it was shared, then from here it becomes invalid.
This guy's a bomb, bro.
So it becomes really weird with what we're working with. But hold on, let me grab my paper real quick. Second. modified. Okay. So you could also just think of it as if it gets modified in one cache, then that means it is invalid in the other. And then on processor 2, we are loading the value in address 3 into R1. This makes it so annoying because you can't rewrite it, so you have to keep going back up to the top, so it makes it confusing. We're on processor 2. Use a pointer. We're on processor 2. And we're loading the value of 3 into R1. We see it's invalid, so we get a miss. But here in processor 1, we have it, but it's modified. So in order for us to share it to processor 2, we first have to flush. Right? So address 3. Goes from modified to exclusive. And the data was 8. So 3 here, 8. Okay. And then once we flush it, then we can share it to processor 2. Okay. So once we share it, shared. And this is allocate and write miss, yeah, so then we could just share it. That would go here. Shared 8. Actually, wait, no, I'm in the wrong spot. Yeah, it's here, sorry. Okay. Does that make sense?
Could you go over this one again?
Yeah, so we're on processor 2, loading address 3 into R1. Look, we see in processor 2, address 3 was invalid. But in processor 1, 3 was modified. So since it wasn't exclusive and in sync with the main memory, where here it's requesting for it to be in sync, we first flush the modified value into main memory. So then it goes from modified to exclusive, where we put 8. And then once we have flushed it, then we can share it. So it goes modified, exclusive, shared. Then we can, again, re-input 3. We share it, put 8. There you go. And then processor 1. We're loading address 1 into R1. We see on processor 1, we already have address 1. It's just modified with value 66. So we can just go ahead and rewrite what we were working with. Address 1 should go here. Stay modified. 66. Okay. Then I don't think anything in the right should change. Because do we have 1? Okay. Then number 5, we're loading R1 into address 1. Okay. And we see that before R1 here was equal to what's in address 3 at this point. And that was 8. R1 here is 8. Okay, for processor 2. And here, processor 2 we have to load 8 into address 1. So do we have address 1? We do not have address 1. Okay. Since we don't since we get a miss on address 1, processor 1 gets flagged because it has a modified value. Since it has a modified value, we want to give the user the most updated value. We first have to flush the value 66 to main memory. So I believe it should be here 66. On number 5. Set 66. So we flush it. And then we have to put address 1 into here. Right. So we find a spot for address 1. That would be 1 mod 4, so that'd be 1. So it's going to go right here. And since this was exclusive, once it gets into here, we can just share it. So it goes from shared. But then we also see that we're then going to go ahead and update it. Right. Since we're updating it, this is going to become modified. And since that became modified, this becomes invalid. And then this gets the value 8. At least I believe it should have value 8. Right? Just tell me if this makes sense. That should have address 3. In his answer, instead of 8 here, he puts 1. Because here, it says you can assume each register is initialized to value 1. But then on processor 2, address 3, that is, sorry, not address 3, R1 is made to 8. And then here, we're still in processor 2 working with R1. So that should be 8 as well. So I believe that's the correct answer. He made a mistake there because he put 1. But, yeah. Okay. And then, let me take a look at what I put again. M to I.
Justin?
Yeah.
On processor 2, you put address 1 on cache 1 because 1 mod 4 is 1? Is that what
Yeah.
that is?
Yeah. Yeah, 66. 1. Okay. Alright. And then number 6. We're loading the address R1, which we know R1 stores number 8. Okay, and we're on processor 2. So we have to check, do we have 5? 5 was here, we had it, but we don't anymore because it was replaced with 1. Right? So now we have to put 5 here. Let's see, do we not have it on processor 1? We don't. So we get a full write miss, and both processors do not have it. So we're going to update that value in our cache, and we know that it is write back allocate on write miss, meaning that we don't update the cache. That's going to be modified with the value 8. Okay. Does that make sense?
Could you repeat it? 'Cause I'm confused.
Here we're on processor 2, and we're working with R1 and 5. R1 stores 8, and we're looking for address 5 on processor 2. We had address 5 in cache 1, cache index 1, but then it was replaced by address 1 here. Now we don't have it anymore. So we get a miss. Based on that miss, we check, does cache 1 have it? We do not have it in cache 1, so we get a full miss. Then from that, it says we have to check out our write miss policy, where it says write back allocate on write miss. Which means that if we have a write miss, we're just going to update the cache and not the main memory. So from here, we're going to put address 5 into our cache, put the new data that was given from R1, and it's going to have modify because we just updated the cache and not the main memory.
Okay, I got it.
And since we're replacing it, and it was a modified value, before replacing it, we have to flush it. So you can think of this location being going from modified to exclusive, and then we're modifying it with the new value of 5. And that's why 8 gets stored here. Okay. But again, he says he keeps putting 1 on his answer instead of 8, which doesn't make sense, but I'll email him about that. Because it doesn't make sense to be putting 8. It doesn't make sense to be putting 1 if we initialized R1 as 8. Doesn't make sense.
Does it have anything to do with the fourth instruction?
Well, that's on processor 1. Here we're on processor 2. And address 1 here, that's stored 66 anyway, so that's still not the value 1. He's putting 1 because it says you can assume each register is initialized to value 1. But then here, we're changing that, so that doesn't make sense. You get what I mean?
Yeah, no, I understand.
Okay, yeah, because this one it was 8 on processor 1, but here we're on processor 2. But the value 8 was shared to processor 2, so then address 3 stored 8. And then from there, that was stored into R1. So processor 2, R1 stores 8. And then from there, R1 is stored into 1, and R1 is stored into 5. And that's why I put that they both have the value 8. That makes the most sense to me, but I guess I'll email him about it tomorrow. Not tonight, but tomorrow. Alright. And then, what else is there? I think we did both spring 2022 and fall 2022, right? I think we finished them both.
Yeah.
I think the last one left is 2023. That's the solution. Okay. Well, this is the long one. Okay. I don't know how to do this one. This one looks weird, but let's see. Okay. Alright, so this one's worded weirdly. It says, consider the following messy code. Consider the following code fragment that runs on a multiprocessor system that implements the messy cache coherence protocol. We have a program, and it says, consider the following order of instructions on 2 processors, P1 and P2, and it gives you the instructions, right? So this question is similar to this. Right? Instead of saying address, they say quotations 3. That's just the address. All right. So on processor 1, we run address 3 into R1. We don't have address 3. Okay. Actually, initial state. I don't even know what you would put for initial state because it's not even there. So I'm just going to put a blank. Anyways. So processor 1, we run load address 3 into R1. We get a read miss, so we're just going to go ahead and grab it from main memory and put it into our cache. So it's going to be exclusive. So boom. Then processor 2 runs the same line of code, and we get a miss, but we also already have that on processor 1. Okay. So then we can just go ahead and share it. Okay. Also, he doesn't specify the write miss policy. Like, which write miss policy should we use? Because he doesn't specify it.
Justin, wouldn't it be shared for both, or am I?
Oh yeah, I meant to put that. Let's just do. What was the one for here? Let's just do write through, do not allocate. All right. And processor 1 runs instruction 2. They do the same thing with address 2. Exclusive SS. And then processor 1 runs instruction 3. This is a ALU operation. It's an R type, so we're not dealing with addresses. So nothing is going to change here. So S, E, S. Okay. Then we're going to run instruction 4, where we're loading R3 into address 2. Okay. R3 into address 2, it was already exclusive, and now we're also updating it again. So be exclusive again. Okay. Hold on, give me a second, let me think. Okay. And this is going to be SS. And then, of course, we don't have anything for 2, so that doesn't change there. All right. Then processor 2, we run instruction 2, which says load load address 2 into R2. We can just go ahead and share that with processor 2 address 2. So now we're at SSSS. Processor 2 runs instruction 3. That's a R type instruction, so that doesn't change anything in our cache. Okay. Then processor 2 runs instruction 4, where we're changing the value of address 2.
Wait, Jesse, can you explain that last one again? The last instruction.
For the R type instruction?
No, the processor 2 on instruction 2. No. Processor 2 on instruction 3, sorry.
Yeah, that's the R type instruction.
So you just repeat S.
Yeah, it doesn't change anything because R type instructions don't have to do anything with memory, or like they don't have to do anything with the cache. We never go to main memory with our type instructions. So that's why it stays the same. Then processor 2 runs instruction 4, where we're giving a new value to address 2, so that becomes exclusive, and then processor 1 becomes invalid for address 2. Shared. Okay. Then processor 2 runs instruction 5. That's another R-type instruction, so we just repeat what we had before. SE. Then processor 2 runs instruction 6, where we're loading that value into address 3. So address 3 becomes exclusive on processor 2, and then becomes invalid on processor 1. Okay. Then on processor 1, we run instruction 5. That's the R type, so nothing changes. And then processor 1 runs instruction 6, where we're loading R4 into address 3. Right? But we get a write miss because address 3 is not there. So write miss, we said do not allocate on write miss. So we're not updating the cache. So from that, this is going to become invalid. And since we updated the address of R3, this is also going to become invalid. Invalid. E. I believe that's the answer. Let me check. Oh, so his answer, he used write back do not allocate. So his answer was IIIM instead of IIIE for the last line. But again, it's different based on what you use. We used write through do not allocate, and he used write back do not allocate. So the only difference with his is that this was exclusive, shared, exclusive, shared. That's correct. Then he repeated shared, exclusive, shared.
Wait,
I'm
Justin,
just comparing this. Yeah, what's up?
isn't write back do not allocate and write through do not allocate the same thing?
Right back allocate. Right through do not allocate. They're technically the same thing, but write through will never have modified bits, where in his case he has modified bits. Write through for any case will never have modified.
Okay.
Right, where I'll bring up his answer. See, for him, he has modified because it's right back. But for us, we have just ease because it's right through. Because anytime a change is made to the thing of it like this, write back do not allocate and write through do not allocate are only the same on misses. But here he has hits, so anytime he has a hit, he updates the cache and not the main memory. That's why it becomes modified. But here we're updating the cache and the main memory, so it becomes exclusive.
Okay.
So it's only the same on miss, not on hit.
Yeah, you're right.
All right. So that's the answer for write through do not allocate. And then answer for write back do not allocate is this right here. Okay. And this kind of highlights the difference between the two. Okay. And this one says, consider the following sequence of operations by two processors on memory address B. Determine the state of that block in the caches of both the processors after each operation in the sequence for the messy protocol with a write-through cache, initially empty. Okay. So he doesn't, again here, he doesn't specify allocate or do not allocate. So we're just going to do write-through, do not allocate. He did specify write-through, but he didn't specify the allocation. So let's just do not allocate. All right. So they're initially empty, and processor 1 reads B. We're talking about a read, not a write. Since we're reading and we get a miss, we just go to main memory, grab the value, then bring it back. From that, E. Okay. And then on the same processor, we write B. We have the value B. It's write through, so we're going to update the cache and the main memory so we stay exclusive. Okay. Then we say P2 write B. P2, we don't have B, so we get a write miss. Okay. And we said on write miss, do not allocate, but update the main memory. So nothing's going to be put here. Anytime something's not put, I'll just do like that. But this will become invalid because now we're not in sync. Okay.
Wait,
Does that make sense?
Wait, it wouldn't be shared, right?
It wouldn't be shared because we're writing. We're not reading.
Okay. Yeah.
Right? And then now we're saying P1 reads B. P1 doesn't have B. And it's a read, so we're just going to go and grab it. That's E. This has nothing yet. Then P1 writes B. Again, we have B. And it's write through, do not allocate. But it's write through, so we're going to update the cache and the main memory. So they're still in sync. And then P2 reads B. P2 does not have B. P1 does have B, and we're reading it, and the P1 inside of B, the B inside of P1 is exclusive, so we can just share it. All right. So that would be the answer. Okay. Let's go ahead and check it. We see we have E, E, I, E, E, S. E, E, I, E, E, S. Okay. Now, I don't know if we have to include those arrows. He does. But just know we have an M there because it's a write. Initially, we're exclusive, then we're modified because we update what's in the cache. And we go from modified to exclusive because once we update to the cache, then we update the main memory. That's why it's EME. Okay. All right. Does everyone understand why this is correct? All right. Then here, 2 more left. I think after this 2, I guess we'll be done. And also, it looks like Clint didn't end up doing the. Oh, no. Yeah, his office hours things, whatever. He's just doing it in the text chat. He's not doing a VC. But whatever. All right. Anyways. There we go. Okay. This one says the cache coherence mechanism for a multiprocessor system is used as a messy protocol with direct mapping. I'll highlight that. Direct mapping. We're using write back, allocate on write miss. Meaning, even if we have a miss or a hit, we're only going to be updating the the cache and not the main memory. And you can see that's true because he does not include a main memory table here, because we're not going to be touching the main memory really. Right? And it says determine the state of that block in the caches of both processors after each operation. So we see for this question he doesn't say for change blocks only, meaning that we can rewrite on each block, making it a bit easier to answer the question. Okay. Let's see what we can do. First part, processor 2 is reading reading 1. Okay. We're reading 1, and processor 2 does not have 1. Okay. So first of all, we have to find a place to put it. 1 mod 4. Right here. Boom. Then 8, 6, 3. And we could just put EMS. Okay. So we're reading it, and we see that processor 1 does have it, but it's modified, so it's not updated with the main memory. So first, we're going to update it by flushing. So we're going to go to E. Let me just write everything else. All right, we're going to flush it, and then we're going to share it to processor 1. The state of processor 1 is shared. Does that make sense? Eric, you good?
Yeah.
Okay. Then P1 writes address 2, meaning we're going to change what's in address 2. Okay. We're only working with address 2 here, so we can just re-put what we had here. Valid, shared. This one doesn't have address 2, so we're just going to re-put what we had before. Okay. And then at this spot here, we say, we are changing the value of address 2 on a write back policy, meaning we're only going to update the cache on a write. So this is going to go from exclusive to modified, because we only updated the cache and not the main memory. Does that make sense?
Could you repeat that?
This is a write back policy, CPU. We're writing to 2. 2 is inside the cache, and it's exclusive. But we're writing back, not writing through, meaning we're going to update the value in the cache and not the main memory. So it's going to go from exclusive to main memory, because now the value inside of the address of the cache and in the main memory, they're no longer in sync. So now it's modified.
Okay.
Because now we've modified that value. Now on processor 2, we write to 3. So let's rewrite everything we had in processor 1, because that won't really change. Eight, 1, 6. We see we have a 3. And we see it's an S. So it's sharing with processor 1. And on processor 2, we get a hit, which is write back. So we're going to just adjust that data, but we're not going to adjust the data in main memory. So who can tell me what it will turn into?
Wait, what did you say?
We are, modified. Because we're on processor 2, writing to 3. And we see on processor 2, we had a 3 that was there, but it was shared with a 3 here. And this is write back, not write through, so we're only going to be updating the cache and not the main memory. So it's going to go from shared to modified because we were modifying the value in the cache and not the main memory. If it was write through, then it would go from shared to exclusive because we're updating the value in the cache and the main memory.
So it
And
doesn't.
since we,
Oh yeah.
what
So
did you say?
it doesn't matter what state it's in. If you're like writing back to it, it's gonna become modified always.
Yeah, depending on what you're doing, I think. All right. And then here, since that became modified, what will the state of 3 become in processor 1?
Isn't that invalid?
Yeah.
Invalid, yeah.
Okay. All right. Now, here, processor 1 reads the value 8. We see processor 2, we do have 8. And it's exclusive. Processor 1, we don't. So we have to find somewhere to put process address 8 in processor 1 with direct mapping. So what's 8 mod 4?
0.
So 8's going to go here. And we can fill in the rest here. And since we have a miss on here, right? But it's exclusive here, right? Then what are we going to do?
You can just share it, right?
We can just share it to prevent going to main memory again. So that shares. And that would be your answer. Let me just put 2, 3, 4. So let's go ahead and double check. Look, it says write back applicant write miss on the top. It doesn't rewrite each part. I like to do it just to be more coherent. Let's check. Number 1, we have 1 MES and then 1 S. 1 MES, 1 MES, 1 S. That's what he has here. 1 MES, 1 S. Processor 2, he has just 2M. Nothing changes here. Processor 3, he has 3 SI, 3 SM. Here we have 3 SI, 3 SM. Processor 4, he has 8S and 8ES. 8S, 8ES. Right. Oh, why was I... Hold on. I can just have this as M. Okay. Alright. That's the answer. Does that make sense?
Yeah.
Alright.
Yes, President.
Alright. And final question. I don't even know how to answer this, but let's see. Show the final state of the system using the Messy protocol for cache coherence. The system has 4 processors, meaning 4 separate CPUs, each of which contains direct mapped cache. So that's direct mapped, direct. These are all caches, and they're connected to each other with the ALU bus, the memory. And they all have 8 blocks. The write through, allocate, and write miss. And this is what we're going to be running.
Wait, is it possible that he'll give us like fully associative and then like direct map on like different CPUs?
I think a system can only have one mapping system.
I was just confused because it says each of which. So like, I wasn't sure if it meant that like each one can have a different one.
Yeah, I think he just worded it that way, but I think in the real world, each processor can only have Each processor has to have the same mapping system. I believe. Don't quote me on that though. All right. System CPU 0. We read 0. All right. But we don't have it. All right. So we have to go get it. Wait. Show the final state. Okay, so we have to go get it from main memory and put it in. So we go ahead and grab it. We're exclusive now. Okay. Then CPU 2, we're writing to 1, but we don't have 1. So on write miss, we have to allocate a write miss. Meaning we grab the value from main memory. Sorry, we update the value in main memory. Or sorry, we update the value in cache and then also update in main memory. Right? So it should go from modified to exclusive. This is for. Right. Oh wait, sorry. This is direct mapping. So this would go here. Sorry. And 0 went there. Okay. All right. And then CPU 3, we read 2. Again, we don't have 2. So we go ahead and grab it from main memory and put it in. Becomes exclusive. I keep putting that in the wrong spot. That's supposed to go here. Direct mapping. All right. Then CPU 1, we write to the value 3. We don't have 3, so we go ahead and get it. We go from modified to exclusive. Right, where we update that value in the cache, and then we also go ahead and put it in the main memory. Okay. So we were on here, and we're on here. CPU 0, we read 4. We don't have 4, so we go ahead and main memory, grab it, and put it in the cache. 4 is exclusive. CPU 3, we write 5. We don't have 5 again. Same thing. CPU 2, we write 6. We don't have 6. Same thing. What the fuck just happened? Same thing. Right? CPU 1, we read 7. We don't have it. There you go. All right. CPU 0. Oh, wait, sorry. Wrong CPU. Okay. CPU 0. Again, we're reading 0. We have it. So that just reads it perfectly fine. Then we go to the line 2. CPU 2. We read 2. We don't have it. Actually, yeah, we don't have it in CPU 2, but we have it in CPU 3. That can become shared. Shared. Okay. CPU 1, we read 7. We already have 7, so that doesn't change anything. CPU 3, we read 6.
Wait, for CPU 1, when you read 7, since it's at CPU 0, do you just share it again?
Wait, what?
For CPU 1, you're reading 7, but it's not in CPU 1, so do you share it from CPU 0?
It is in CPU 1.
Oh, wait.
It's in CPU 1 here and here.
Uh-huh. Wait, I'm confused.
7 was never in CPU 0, it was in CPU 1. We got it here,
Oh, yeah, see,
and then we also read it again here.
yeah.
Then CPU 3, we read 6. We don't have it. But CPU 2 has it, so we can just share it. Okay. CPU 0, again, we read 0. We have it. That doesn't change anything. CPU 1, we read 1. We don't have it, but CPU 2 has it. shared. Okay. And then CPU 2 reads 0. We don't have it, but CPU 0 has it. Shared. That should be the final answer. Does that make sense?
Mhm.
So let's go ahead and check. What is 0? Oh. Oh, that's just okay. I don't know why he did that, but whatever. So 0 is ES, then E. Wait. 7. Why does he share? Why does he share S to 7? We never call CPU 0 7. I think he made an error there. I don't think he meant to do that. That's not correct. Because it's not correct because we never read nor write. Actually, it's shared, so we never read 7 on CPU 0. Or am I tripping? Am I reading incorrectly? Someone double check that. I believe I'm right.
Yeah, I'm pretty sure you're right. I don't see CPU 0 read 7.
So that should be blank. Then 1 is 7. Then we have E. Yeah, then he shares it here. But that's incorrect. That the final state should be E. Okay. Wait, 6. Hold on.
What?
Wait, what the fuck? What is bro doing? CPU 1 6? When do we do CPU 1 6? We do CPU 2 6, CPU 3 6. We never do CPU 1.
I think he's tripping, honestly.
Yeah,
Buddy
this is
suck, bro.
yeah, this is incorrect. He did it wrong. Unless this is the one that he said that's incorrect. I don't know. But this should be correct. Let's see what else he does. CPU 2 shared. The fuck? For some reason, he never shares 2 either. Which it should share. Yeah, because we read 2 on CPU 3 here, but then we also read 2 on CPU 2. So it should share, but he put both as exclusive. Yeah, his answer is really wrong. What the fuck? I think he did that on purpose. Legit, the only thing right is like the bottom right one, the top left one, CPU 1 1, CPU 1 3, CPU 0 4. Yeah, there's not a lot. There's not a lot correct. Sorry, what happened?
For CPU 1 through cache size 3 or cache 3, right? That why is it going from modified to exclusive?
So CPU 1 3.
Yeah.
So here we're writing 3, right?
Mm-hmm.
And it is write through, allocate on write miss. So we get a write miss. The first thing we do is allocate. So we put it in the cache, and it's not the same values in main memory. So first it starts off as modified. Then we go update main memory, and once we update memory, then it becomes exclusive.
Oh, so
That's why
due
it's
to the
modified exclusive.
policy. Okay.
Yeah, due to the policy. That's why it does that. Yeah. anything, anytime you're allocating, just remember that you're updating cache first, and then if it's write through, then you're also updating memory after updating the cache. That's why anytime you update cache, it immediately becomes modified. But if you update memory after that, then it goes from modified to exclusive. If that makes sense. Right. And I think that's it. I don't really have anything else to go over. I don't think there is anything else for us to go over. That's like it.
Yeah.
But is there any other questions about any of the other questions we went over? Nope. All right, then I think that's it for 343. Did we still want to do 320 or no?
I don't know, because I'm looking.
Yeah, I'm mad tired already.
Watch right now. I mean,
If
can we do
Mm,
tomorrow? If
Tomorrow?
you are like, yeah.
Tomorrow I'm doing something with Code Resolve at 2 p.m., but I couldn't do anything afterwards.
Yeah, I mean, if everybody is, free, available at that time, we can do it after 2 o'clock or whenever you're free, Justin.
Yeah.
Tomorrow.
That should be fine then, because I want to watch One Piece tonight as well. That shit comes out at 10. I don't want to be doing 320 when that shit comes out.
I bet.
Yeah.
Bet. So
So,
just text us in the chat, I guess, right? Like, just add us when you
Yeah.
are ready. So
mm.
get started.
And was